Remember, our target here is to determine whether our sequence is convergent or divergent. Do the terms get close to some number? Um, uh, but what if they give you your sequence as a list of numbers like this instead of some sort of explicitly defined equation? And that equation is what we want because we're going to take the limit as n goes to infinity. That means that you're going to first have to come up with that equation, which involves some sort of pattern recognition, some inductive reasoning. And for some of us, that can be kind of challenging. So let's take a look at a couple of these sequences here. I've got 1/2, 1/4, 1/8. What do you think the next term is? Well, most people would look at this and look at the denominators and go, hey, we're just multiplying by 2. 2 times 2 is 4, times 2 is 8, so I'd expect the next one to be 1/16. Those are just like powers of 2 on the denominator, right? Okay, and now if I take the limit as n approaches infinity, then the bottom gets incredibly big. As the top stays at 1, this should be approaching 0. So our terms, individual terms, are converging to 0. That's a good thing. That's actually what we want. All right, but I can change this 1/16 to something else. Turns out 3 terms, not always enough to figure out what the pattern is supposed to be. So here, look, the first 3 terms are identical, but now I'm going to change this to 1/15. Messes everything up. It's not exponential anymore because obviously this is not a power of 2. Those work, but this one, not so much, right? So how are you supposed to come up with this function here for these terms? Nothing like that is going to be on the AP exam. This is just for, illustration purposes. Probably what you'd have to do is just the denominators here, maybe do some finite differences. You remember that from Algebra 2, or maybe do some sort of polynomial regression model on your calculator to come up with it, but there it is. So let's say we're going to take the limit as n approaches infinity. The top degree is 0. It stays the number 6, but the bottom keeps getting bigger and bigger and bigger. It's actually 3rd degree if you were to FOIL this thing out. So that should also approach 0, converges to 0. All right, let's try another one. So still same 3 first terms, and then here we go with 7/62 for the 4th one. What? And look how nasty this thing is. What? So this one would be extraordinarily hard to come up with that function for sure. But let's say that we did have that function. Now we can take the limit as n approaches infinity. It's rational, so we can use some pre-cal rules. We have squared over squared, which means we just take the ratio of the leading coefficients, 1/9, so it should be converging to 1/9. So all your terms are getting closer and closer to being 1/9. All right, and then got one final one here, changing that 4th term to a 0. Okay, and then there is the new function that comes up with it. So this is just to illustrate the fact that sometimes coming up with the functions for these things is kind of challenging, right? After we get the function, then, oh, the calculus part is so easy. So what would this converge to, if anything? The top, if you were to FOIL this thing out, would have a degree of 3. The bottom has a degree of 2. Top gets bigger faster than the bottom. This does not converge. It diverges, goes to infinity. All right. So here's one that I think that we can figure out. Let's take a look at example 7. Determine whether the sequence a sub n converges or diverges, and you can see it's just defined by an ordered numbered list like this. We got 2/1, -2/1, and then 8/4, or 8/2, I'm sorry. It simplifies to 4, but notice that these things haven't been simplified. They haven't been simplified like reduced just because it makes it a lot easier to come up with a function for this one. So the first thing that you should recognize, the easiest thing, I think, are the denominators. 1, 2, 6, 24, 120. By the end of this module, I really hope that you have those numbers memorized, like totally can recognize that those things are just factorials, right? This is a 1 factorial, 2 factorial, 3 factorial, 4 factorial, and so on. So the denominator is just n factorial. Okay, we have that. All right, next we're looking at the top numbers. We got a 2 of 8, 26, and 80, and 242. Well, they're all even. Well, there's something. And we might think that they're powers of 2, which seems to work for the first 2, but it doesn't work for the third one, so that's a problem. So it's got to be something different. But notice that these numbers are actually really close to some other numbers which are much more helpful. So 2 is close to a 3, 8 is close to a 9, 26 is close to a 27. Instead of 80, we want to think 81, and 242, we want to instead look at 243. All of those numbers, I bring them up because they're powers of 3, and all of our top numbers are just one less than that. It's one less than a power of 3. And sometimes it just takes a bit of practice before you can recognize something like that. So you can write that part of the function as 3 to the n and then minus 1. And then we have one more part, and that is the fact that our terms are alternating, starting with a negative, and then a positive, and then a negative, and then a positive. So we want to put our alternator in there, and we've got a couple of options. Is it -1 to the nth, or is it -1 to the n plus 1th power? Well, our very first one, if we stick in the number 1 here, so like for example, if I stick in 1 here, 3 to the first power is 3, minus 1 gives us 2, so we must be starting at 1. If I stick in 1, I need it to be a negative number, so that's going to be -1 raised to just the nth power, and so here is what that final function was going to look like. So -1 to the nth, and then multiply that times 3 to the n minus 1, and then divide that whole thing by n factorial. Okay, so now I think that we are ready to determine whether or not this converges or diverges by taking the limit of this. Whoops, I'm on the wrong part. All right, let's add an extra page in here. And looks like I'm going to write in red, which I'm totally not. Let's get this delightful blue color. Okay, so we have our explicit equation for our terms of our sequence. We're going to take the limit as n goes to infinity, -1 to the nth, 3 to the n minus 1 over n factorial. All right, so remember the first thing that you ordinarily do when you're evaluating a limit is you stick in the infinity or whatever it is the limit is approaching. And that's a problem with this term right here, which I sort of erased. If you stick in an infinity here, this just keeps alternating, -1, +1, -1, +1, off and on, off and on, off and on, which is why we apply the absolute value theorem. If this thing is convergent, if this is going to converge, then that means that the limit as n goes to infinity of the absolute value has to converge. We want to check that one instead. So we're going to take the absolute value, -1 to the nth times 3 to the n minus 1 over n factorial. So what does that do for us? Remember that this thing here is only the number +1 or -1, depending on what the value of n is. This is always going to be, for these large numbers, this is always going to be a positive number, right? If I'm starting with the number 1, it's still just a positive number. It's always positive. This is positive, so the absolute value does not affect this. It only affects this piece, which turns it into the limit as n goes to infinity of just 3 to the n minus 1 over n factorial. Now what happens when we stick in infinity? So we would have infinity on the top, we'd have infinity on the bottom. You can do L'Hopital's rule, but not really. Just think in terms of relative growth rates, which one grows faster? And that's going to be the denominator as a factorial grows faster. Faster growth. Meaning that this thing should converge to 0. Also, like I said, that's a good thing whenever we get into our series. We want our individual terms to converge to 0, like this. What's a series again? If you don't remember when I hinted at it in another video, that's what's coming up in the next lesson. Anyway, so we're going to end this one right here, and then we're going to take a look at some other kind of sequence, other kind of very popular sequence that we see on calculus exams.